Okay, so what do we want to do? Who was at the talk yesterday when I talked about the attributor? Okay, so most of you know what to expect. It is a framework a fixed point iteration framework, initially built to deduce attributes. That is where it had the name, and I kind of stuck with it, even though it does more than attribute deduction nowadays. So this is a tutorial where I wanted to show you how to use it. And I figured, I thought for a long while what to do, and finally settled on, let's define a new attribute that doesn't exist yet, but I want to propose for LLVM. I'll show you briefly what that means to add a new attribute, because we should add more. Then use that attribute in some other part of LLVM to actually get better results. What we will do is we use it for alias analysis. So we will use that attribute to improve alias analysis. And then after, we will derive that attribute from, we will go and actually derive that attribute from source and propagate it using the attributor. So we go full circle. You will see everything from creating a new one, using it, to actually deriving it. OK, so as you can see here, the attribute is called max object size. That is the name of my branch, feature max object size. So we will derive how big can an object be that a pointer points to. Why is that important? So let me open something for you here. Basic alias analysis. So the basic alias analysis has a function. So this is already with the patch I'm going to show you. So it says, if the size of an axis is larger than an entire other object, then those two cannot alias. The idea is, if you have two pointers to two things, one of them is at most n bytes large, and the other one is for sure larger than n bytes, those two things cannot be the same. There's no aliasing between them. So basically, large objects don't alias with small objects. That's the idea. Okay, so if we can keep certain size information about things, we can use that for alias queries. Initially, this code looked a little bit different. So this stuff wasn't here. It did something. It said something like this. And what it actually was doing is, if the object was if you could see the allocation side at this point, in this query, when inside alias analysis, if alias analysis could see the allocation side, and somebody said, does this allocation alias with the following pointer in a certain size? Then it would say, OK, if the size that I was asked for is bigger than the allocation, then it does not alias. That was the logic. And then a few weeks back, I added this part about the minimal size, where it doesn't necessarily have to only look at what the query is in regards to, is it aliasing up to a certain size? But if the pointer is known to be dereferenceable up to a certain number of bits, which means the object underlying is actually at least that big, you can use that information as a lower bound on the size of the object. So if you see the allocation of one, and you have a lower bound on the size of the object of another, they do not alias if the lower bound is bigger than the complete size of the other object. Does that make sense? That is what LLVM already can do now. I added that a couple of weeks because we started to deduce more and more attributes in the attributor, including dereferenceable, and I wanted to make use of those attributes. So we have to get our hands dirty and teach certain parts of LLVM about those attributes to actually use them. So we did that. That was great. And today we will add the last part is, you actually do not need to see any allocation. If you just know that this pointer is at least points to something that is at least this big, and this pointer points to something that is at most this big, and if these numbers have a certain relationship, those two things cannot alias. So we want to add this get maximal extent here. And then we say if the maximal extent of the first object is smaller than the maximal extent of the second, or if the maximal extent of the second is smaller than the maximal extent of the first, they do not alias. How does that get maximal extent look like? It basically says, the upper part is the important part, this part here. It's a value. Just ask the value how many bytes it knows the underlying object has. For like the most conservative answer here is like it's infinite. Like the the object is like really big. The most conservative, like the best answer would be 0. Okay, so please ask questions and shout something if you want to know something. This was just like the introduction in what we're going to do and why. And now let's look a little bit. No, I don't want to save my changes. Wait, what did I change? Sorry, shouldn't have changed anything. Okay, let's go and look at these things. Actually, I don't have to rebase. I can just adding a new attribute. First step. Introduce the max object attribute. So this is my local patch to introduce this new attribute. And it is a lot of plumbing involved. I think I had to touch 11 files in total to add a new attribute with the actual getters and setters all over the place to match existing attributes. You don't necessarily need all of that, but if you want to have kind of similar functionality to the existing ones, and what I use here as an existing one is I basically grabbed the whole source code for dereferenceable, which is a lower bound on the object size, like from that pointer, and this is an upper bound, so it's very close. They should like have the same functionality in terms of getters, setters, and where you can put them and what you can do with them. So I just grabbed everywhere dereferenceable, and I then copied that for max object size. So you start with adding an enum into the list of all attributes. So we just recently crossed the threshold of 64 attributes, which was a big deal, because up for a few months ago, we were not able to actually represent more than 63. That happens. But now we can like have an unlimited amount. So we solved that problem. Now we can like add more. It's actually fairly easy. Then you have getters and setters all over the place, mostly like arguments, call, function return values, all of that. It's fairly boring, most of it. Like I will skip all of these getters that are not that important. Again, if you want to do something like that, look what the closest attribute is we have that matches yours, grab for that name, and start looking at those files. And that is not only a trick you do for attributes, whatever you want to add. A new intrinsic, look what the last intrinsic that was added does, or an intrinsic that is close to what you want to do, and so on and so forth. That is because it's really hard to get it right. And when we started over the summer adding attributes, like no free, no sync, people were confused how much plumbing is involved. And like our reviewers were like really surprised. So it takes a lot. So you look where everything, where things are set and not set. Most of it is fairly simple. This is the TD file, like the TableGen file. This is actually like the new attribute. So it's like one line. It says, okay, max object size is now a new attribute. Everything else is just like setting things and making sure you can move it from attribute sets to attribute lists to attribute builders, and then merge them, remove it, and on and on. So there's a lot of just moving parts involved that you actually don't really care about. Now, this part is what happens if we want to print the attribute, because at some point we want to like put them in IR. So we have to have a keyword for it so that the lexer and the parser know what to do. Again, max object size is very close to dereferenceable, so I just like every time dereferenceable, I copied it, renamed it. Here, same thing, parse optional deref attribute bytes. If you see, wait, like there, upper part, third line. I didn't even bother to rename the function. I just like parses a number, like parentheses and number. So like you go with that. All of that is fairly straightforward. Questions? No. Okay, so we did that. And there is like this one wonderful file that has all the attributes in them, and which basically is a test that we can read them and print them out again. Like it is a file that just like reads it in various formats, like dumps it in like binary format, reads it again in, and like prints it out again, such that we make sure that all the readers and writers actually handle all the attributes well. So if you add one, you have to have a test in here. So you see how it will look like. You can manifest it at the function return level. For this point, then it's this pointer that has a size of at most 8, and at an argument level. So this one has a size of at most 8. Okay, that's how you can like manifest it. The same for call sites, call site arguments, call site returns. So it's an attribute for values. Okay, so we have that. Now, let's look at the test cases for the alias analysis. Just which one is easy? Which one is easy? This one is easy. Okay, so let me remove everything that you don't need to see. So that one. What do we have here? We have 2 arguments. One has a maximal object size of 6 bytes. The other one is dereferenceable 7 bytes. So that is the situation. One is like smaller for sure than the other one. And we test that alias analysis will say no alias between the 2. We also have tests further down where we remove one of these attributes and we make sure that alias analysis says may alias, because like alias analysis doesn't know anything about those pointers, right? There's an external function that takes 2 pointers. Everything it knows is encoded in those attributes. So, sure? The question is dereferenceable 7, what it means. It can be bigger. Dereferenceable 7 means I guarantee you that you can access the next 7 bytes through this pointer, from this pointer, without trapping. It can be like arbitrarily big after that, but that object will be 7 bytes from there. But max object size says, I guarantee you that the underlying pointer is has at most like 6 more bytes. It could be null. It could be like a dangling pointer. It could be whatever. Like you're not allowed to access based on max object size, but based on dereference object size you can, which was introduced to do things like loop invariant code motion, where you hoist a load out of a loop. Because you change control conditions, you cannot just do that because the pointer could be null or dangling or whatever. But if you know it's dereferenceable, you can do that. Okay? That was the main idea about dereferenceable. You can use it for other things as well, but that is one of the ideas. Okay, so this is like we have a couple of tests here where we make sure that everything that actually the things that we want apply. Questions on those? Okay, so now let's look at. Okay, I've shown you how to reason about aliasing. Oh yeah, so there is already the notion, like a way to compute the object size of an object in LLVM. That was added for the sanitizers. But that logic is fairly complicated and it's supposed to like compute the exact object size. So probably once I add this, I actually want to kind of combine those two and make them like work together such that it like the get object size gives you potentially the exact thing or range or other things. But for now, I skipped that part and instead went with something that looks very much like what dereferenceable looks like. And dereferenceable has this, a value has this function. This is, any value has this function. So any value means any instruction, means any argument, means any function. Like it's value in the LLVM class hierarchy, which is up there above everything. And that value has the function get pointer dereferenceable bytes, which is supposed to return the number of dereferenceable bytes of that pointer, if it can determine that. 0 is like the unknown. And I made like a similar interface, get pointer and max object size in bytes. Okay. And then the implementation is so far fairly simple. You say if it's an argument, look if you have the attribute, like this line I'm on now. If it is a by-value argument or a struct return argument, we actually know that it has like the extent of the struct type. This is a slight hack. You have to deal with alignment here and a couple of other things. Like this is not completely correct, but I didn't want to go into detail here. So basically, if it's a by-val argument or a struct return argument, we take the type of the pointee, which is then like a struct type, and or any value type. And if that type is sized, we can use the type size. Then if it's a call, we look at the call return attribute. If it's an allocation, which is not an array allocation. Why is that? Because array allocations can have like n elements. So, and we don't like kind of give you a number. So we just like skip the part that it could be an array of constant size, another part of the logic we could add. And we just say, if you allocate a single object on your stack, and that object, like the type of that object is sized, we can just take the size of that type because that is the maximal object size, because it's exact object size. And similarly for global variable, if the global variable has a size that is a type that is sized, we take that size. Okay, so this is the getter here, and now we get to the actually interesting part. How does working with this in the attributor look? This is the abstract attribute you have to add, or you should add to the attributor interface. So you say, okay, I have a new abstract attribute, AA max object size, which is an IR attribute. It's a class that offers you a little bit of convenience for anything that is actually an IR attribute. So this is one, so let's use that convenience. And it is also an abstract attribute, which is actually the class it implements, and that is like everything works through abstract attributes. Abstract attributes basically have to provide two things plus a couple of methods. The two things is a position, like if requested, they have to say like what is the IR position they're associated with, and a state. What is your abstract state? For this object, we use the decrementing integer state with 64-bit unsigned integers as an underlying type. So the state is an unsigned integer with 64-bit, which will decrease. These abstract states for integers and booleans are already there, and they will make sure that you don't they will restrict on what you can do with them, such that you cannot accidentally shoot yourself in the foot. So if you want to look at them, we can can go here. So this is the interface for the decrementing integer state. It is an integer state base, which we can look at in a second. If you look at how it inherits from them, the first 0 means what is the best potential value. Like if the object has a maximal size of 0 is the best thing. And the second bit inverse 0 means what is the worst value, like kind of infinite, like the biggest thing that we can have. And then you can take an assumed maximum and take a known minimum, where basically assumed and known are two, like we do a fixed point iteration, but we, if you imagine the integer lattice with all the numbers, we actually do two iterations at the same time, one from above with an optimistic value that we try to find the least fixed point, so the best fixed point we can, and one from below where we accumulate information and try, in case we not reach a fixed point with the above iteration, because we reach a timeout or anything weird happens, we can still fall back on whatever result we computed in the second one. And while we're, this computation is usually for free because the expensive part is traversing all the IR infrastructure, like traversing all the call sites and so on and so forth. So tracking 2 numbers instead of 1 is actually for free. Okay, so integer state, we go further. An integer state provides a couple of methods. These ones are the ones important. Valid state is everything that is not the worst state, because if it's in the worst state possible, like, yeah, there's like you didn't learn anything. The worst state really means nothing. Like and then we call that an invalid state because we then can like give up on these things. A fixed point state is reached as soon as like those two values meet. We can force them to meet with by indicating a fixed point, either an optimistic one where we say, okay, we know that the fixed point iteration that comes from above, that comes with an optimistic value, actually reached a fixed point, so we can, nothing changes anymore, so that is the actual value, so we can just like move the known value up to that value. Or we have to indicate a pessimistic fixed point, for example, if a timeout is reached, and then we say, okay, we give up on the optimistic fixed point iteration, and we just take whatever the pessimistic one computed. And then you can ask for the current values, and you get a couple of like comparisons, equalities, inequalities. So, okay, let's go back to our max object size. Get state just returns the internal state of that type. Get assumed max object size, get known max object size just wrap around these getters of the state. So they return the current values in known and assumed. Anything like you don't have anything else usually in this like public-facing interface. So this is how the world, which means anyone, interacts with your abstract attribute. This is all they can see, all they are allowed to see. Okay. Now internally, what you do. Okay, before we go to the implementation, let me show you how you wire things up. We have these helpers here. You see these are macros that we invoke for certain things. The way things work is, if you request information for a certain position, like give me the alignment of this return value, give me the dereferenceable bits for this argument, it will look at the position, and it will look in the cache, like the position and what kind of information you required. It will look in a cache. If it didn't find that, an abstract attribute for it, it will create one that it will then use to like update and like expand your search of good information. And in order to create one, it has like you basically need like a switch and a couple of new statements and so on. So we actually have these macros that are just give you the switches. Because not for all positions, all attributes are valid. So for example, a function attribute is not valid to create for an argument. And this just makes sure that if you ever try to do so, you run into an unreachable, and it will like give you an error message and tell you, no, you cannot create a function attribute for a value, or vice versa. So we create value abstract attribute for position, means we can actually look at it. Create value abstract attribute for position is what I chose for the max object size, and it will be invalid for an invalid position, a function position, or a call set position. So those things don't have a max object size. A floating value, like any instruction, a global variable, whatever you have, has a max object size, potentially, an argument, a return value, call set argument, call set return. Those things have max object sizes, so that is what this thing says. So you have to create this switch. What you also have to do is, this is plumbing. You have to initially seed these abstract attributes. So you have to say, for which actual locations are you interested in? So this is a loop. Let me scroll up a little bit. This is a loop over all arguments of a function. And for each argument that has a pointer type, we will try to derive all the attributes that deal with pointers, non-null, dereferenceable, and I added to that list max object size. So if it's a pointer argument, we will try to derive that for all of them. You can seed things differently, but the seeding is basically where your like search starts, and then from there on it will expand potentially. So if you're only interested in a single value, you can only mark that, but it will look at the things incrementally where you have to look at. And we also seeded the return values of functions. Here the return type is a pointer type. We seeded there, and I think that is all I did. Yeah. But you see that in our current configuration, identify default abstract attributes, we seed everything. We try to like derive everything for everything, just for the sake of testing and to the sake of like, let's see where we are. In a real production, you probably won't want to do that. You want to like use PTO or other heuristics to like seed things. You don't want to necessarily for every function need to know if there's alignment of a pointer argument. If that function potentially doesn't have loops, the pointer alignment of that might not make a difference. So you want to be careful, but for now, for testing and for development purposes, this is actually pretty fine. And that was all the plumbing you need to get an abstract attribute in the attributor. Now you have to implement the abstract attribute. Let's do that. First class you would probably write is one that looks like this, which is the impl class, which already overrides some of the existing or non-existing functions in an abstract attribute class. In this case, get deduced attributes and get a string, which just a get a string takes the known and the assumed value and prints it out nicely. And get deduced attribute says, okay, if I'm currently not in a bad state, I can actually create a new attribute, like LLVM attribute, and then put that into this vector. And the fact that we, if you remember, this class here, max object size, inherited from IR attribute. IR attribute already knows how to place, like how to put attributes, LLVM attributes into the IR. It knows how to compare them with existing attributes. It will not place them if they are worse than existing ones. It will not like place them if they're invalid. It knows how to place them at the different locations because that is a little different everywhere. So all of these nastiness goes away. You just say, okay, this is an IR attribute, and it will place them for you. If you have an attribute that doesn't have an integer associated with it, like let's say no free, will return, no unwind, all these Boolean attributes, you don't even have to overwrite the get deduced attributes thing. And I probably, like we have to like work on this. Right now, for integer attributes, you have to overwrite there. For enum attributes, you do not. Okay, that is just the first inheritance level. Now, we actually have to provide one class per IR position that we support. Again, let's go down here. What were the IR positions we support? That is floating, argument, returned, call site returned, and call site argument. So floating, argument, return, call site return, call site argument. All these positions, for each we will have to produce a class with a certain name because like in the macros, everything has like a certain naming scheme. And then each of them, like they don't have to do different things, but the classes have to exist. Okay, let's take a look. The first one is the most, like for now, the most important one, the most complicated one, which is floating. Floating is any value. It's just like a value that is nothing else. Like if it's not a call site, which then would be the call site return, if it's not an argument, it's a floating value. It can be just a global variable. It can be like an instruction, a get element pointer, a bit cast, a phi, whatever. It's a floating value. Floating because we don't distinguish at some point there because we can't annotate those values anyway. All the other values have separate classes because we can annotate them, and they have attributes annotated. So that is why we have classes. Maybe we have to like split this up, but for now everything else is floating. Internally, you could like now do different things depending on what the underlying value is.
Sorry, may I ask?
Yeah.
So if I want to have an attribute for basic block,
yes.
what do I do?
We don't have basic block attributes, right? What do you mean?
Okay. I want to. Okay.
We have, for example, we have attributes, abstract attributes here that don't correspond to actual attributes, that don't have an IR correspondence. And then it depends on what you want them for. Like some of them, for example, we have them per function level. And like liveness we just have one per function, like one abstract liveness attribute per function. And then you can ask that about the liveness of a block. So it keeps the tag. But for example, value simplification, which is like constant propagation and so on, we have that per value. Like here, like this one. Like per value, there is a simplification attribute. So that because then like simplifying values is like every kind of value you simplify them differently. You look at different things and so on. So this like abstraction makes sense. But for liveness, it's more holistic about like you look at the whole function and you holistically look at it.
So for function attributes, right?
Yes.
When I have a new function, we have function attributes.
Yes. So we can look at one. So we have
No return, I guess.
yeah. Let's do no return. So wait, let's start down here. So the switch for no return looks different. It basically says everything is invalid except the last two, which is function and call side. Like every function attribute goes on a call side. So those two are valid. Everything else is invalid. And this is the no return implementation, where you have the impl class. Here we actually overwrite the initialize because that should actually go in. That's the get as string as we had before. We have an update implementation here, where what do we do in every update step? Let's skip that. Let's skip over that for a second. Then we have the two classes that we need. I said for everything you need an explicit class. We have no return function on the top, which actually doesn't do anything, but it just inherits all the functionality. But we have to have the class, and it actually is nice because this track statistics has statistic counters, so we track the right statistic counters. It's fairly nice. And the no return call sites for now actually just takes the value of the callee, if there is a callee. And you see the big to-do. Once we have, actually now that we have value simplification, we can do better. And that is what the big to-do says, that now once we can specialize per call site, but for now we didn't do that. All of these things just like transfer, or most of these function things just transfer information from the callee of the call site to the call site. And if while we're at it, we can look how no return works.
So you mean if you have two callees, one is no return, then for this function is no return?
No, it's like each call site is on its own. Like a call site can have.
On each call site, but if I cannot use it on function itself. So if I
This is basically what happens. This is the logic that decides if a function is no return. Let's go through that.
okay.
So you will call this update impl on the no return for the functions until like a fixed point is reached. Nothing, like update impl says unchanged, returns unchanged, and all other things return unchanged. Okay. So what does it do? It first asks if we already it asks for the will return attribute, because if the will return attribute is known, we know it is not no return. So this is just a way out. So if as soon as we know it's will return, give up on no return. Those two contradict each other. Like it can be neither, but they cannot be there together. It's impossible. Okay, so those are the first 3 lines. And then what do we have here? So we have check for all instructions in this line, which says, hey, attributor, please go through all return instructions that are currently considered live and call this predicate on them. And the predicate just returns false. Because as soon as one return instruction is live, we consider the function as not no return. And as soon as the predicate returns false, the check for all instruction aborts and returns false. So as soon as check for all instructions return false, we indicate a pessimistic fixed point, which will say, nope, I don't, this is not no return, I give up. That was it. And in the other case, we didn't encounter any live return. What happens is we will just return unchanged because it's a Boolean thing. Either we couldn't justify no return, then we're done, or we could and then nothing changed, because we started optimistically with no return. Yes.
Check for all instructions means checking the function instructions, or what's the?
Yes, that will check all the it will use. We pass this right, this pointer. It will use this is the abstract attribute that has an associated position. It will use that position to determine in what function, we're interested in, and iterate over the instructions in that function, but use liveness to filter out things that are considered dead. We have various of these check for all things that do these like implicit liveness checks and a couple of other nice things for you, which you should always use if you want to program in this framework, because it does a lot of neat things. And there was one more thing I wanted to say and I forgot.
Well, maybe if I have a programmer is providing no return attribute on the function.
Yes.
Somewhere here it's going to be checked.
Yes. This is, so AA no return, this is the abstract attribute, the generic thing, and it says it's an IR attribute, yeah? That is what it says, okay? Let's get a look at IR. And it says it's an IR attribute, and the next template parameter is the actual LLVM attribute enum. Attribute : no return is an enum value in the big switch. So if we go into IR attribute, it has this helper here, initialize. So IR attribute offers you an implementation of initialize already. Initialize is called when the attribute is first created, the abstract attribute. It was to like make the internal state consistent. But you can do other things, including you can look at the associated value. And it has this helper function, has attribute, which will then look, has the associated value the attribute in question already? If so, indicator optimistic fix point. We're done. We're finished. So if you already have a no return, update will never be called because it has a fix point just after initialize and it will be fine. And this is the layers of IR attribute gives you a lot of niceties, so you should use that. The lower part here is how to deal with non-exact definitions, which are problematic. You can't derive across no exact definitions except attributes that are existing. And the lower part here makes sure that you don't accidentally do so by invalidating your attribute if it is at the function level boundary of a no exact definition. The neat thing about this is it allows you to derive stuff inside a non-exact definition, but you cannot use it across the boundary to call into another, like from another non-exact definition, because that could be replaced. But inside, you can do all the deductions you want. So all of these like weird things are already like handled for you. But good questions. If you have more, please feel free to ask. So we can go through anything. We don't have to like go through my max object size attribute. Sorry. Talking about which, let's go back there. Okay, so we were here at the floating thing. For now, this is actually not what you're supposed to do, but this is just like an initial implementation of the floating update. What I said is, this get associated value gives you, like looks at the IR position and gives you the associated value, which could be like an argument, a pointer, a global variable, whatever like the position was created for in the first place, right? Then we strip some pointer cats because we really don't care about them when we talk about like max object size. And then we say, whatever is left after, give me what is already known at that location. So this doesn't use the fixed point iteration framework at all. It just says, I'll take whatever I know right now. Then you get a max object size. You say, okay, this is a known value because I asked like this get pointer max object size in bytes doesn't deal with assumed optimistic values. It deals only with known values, part of the IR. It looks at LLVM-IR instructions. It looks like global values. It looks like bival arguments and so on. So this is a known value, so you can actually push your known value up. And then we give up. We say, OK, actually, we don't have any logic here. This is just like a mock-up. So this basically just extracts information through some helper function in LLVM. which we do all over the place, but usually we do more smarter things than here. Okay, what about the others? So we need more locations. For example, we need a return value. How do we derive stuff for a return value? We have a helper for that because it turns out for a lot of things, it repeats all over the place. You do always the same thing. For a returned value, we have this helper class, which is called AA returned from returned values. So it will take the state of all the returned values of a function. It will join those states, and the new formed state is the state of the returned value of the function. If you've seen my talk in the very beginning, I had this example where the returned value type, the return type alignment was made up of the alignment of the returned values, and this basically does that for you. So if you don't do anything special, just want to propagate, merge all the information and propagate it, you can use one of these helper functions. They provide the right update methods. Then for arguments, we have something similar. An argument, we just propagate information from the call side operands. Okay? We could use bival information here, which we right now do not. How would that look like? Because, again, if an argument is annotated as bival, it means it is actually copied. A copy is made at the callee. And it has, for that to happen, it actually has to be, it actually is only that big as the copy is. So what you can say is, in order to make this happen, you would, because the bival is a property that is there or not, so you will not put it in update, but you put it in initialize. You would overload initialize. You would say has attribute if it has the attribute bival, then go to an optimistic state. Oh no, sorry, we can't do that. We have to set the number. Sorry. So we would say get state, take known maximum, get associated value, get pointer. Actually, we can do this. We can say, okay, because it has the bival, we know that get pointer max object size will be able to use that information to get us the right value, and we can just say this is as good as it gets because this is exact. So get state indicate passing finish point, and otherwise we will actually want to call copy this. What we actually want to do is we want to redirect to the initialize of our superclass. So that you would do. Now, if you have an argument that is bival, you will actually immediately use that information and not try to move information from the call sites to the argument. Otherwise, it will look at all the call site operands only if all are known. If it's an external function or the call or the function is used in a weird way, which is not a call, it will give up. These helper functions kind of do the right thing for you. If they can't come up with the information they need to combine, they will not and will give up. So then we have, what does an argument do? A call site argument. A call site argument is very often just treated as a floating value. We just use the floating value logic, which is just a value. It could be a real value. It could be 5. It could be a global value. It could be an instruction. So we treat it as a floating value. Whatever the floating value does, we do it for call site arguments. And for call site returns, we copy over the state of the function return. Again, with the big to-do that says, once we can specialize for call sites, we can specialize here. Okay, this is the base implementation. Now you have something that actually deduces max object size on things, not in a real fixed point iterations, but it copies information over from various places and tries to come up with something good. So let's. Oh wait, we had a test for this. Oh no, we didn't. Oh, we do. Sorry, forgot that I already did that. So we have a. Oh, this is the test for the alias analysis. My bad. Test transformation. Okay, let's get a head start here. Let's remove some of them. I really don't like that. Maybe we have to actually create our own tests. Sorry for that. Okay, so let's write an own tests. So we have a function that takes an I32 pointer. Let's call it arc. We do, and it takes an I1, C, branch I1, C, label, and label else. Then is right 32 pointer arc else call at test1 C. Oh, sorry, I1 here. Okay, so we have a test very much like the one I showed in the talk, where we have like a recursion under some condition. This is obviously endless, but that is not the point. And now, okay, let's try to run this. Let's first get rid of the verifier here, get rid of a couple of options. Okay. Sometimes attributor. So right now the attributor always runs, but it is it has a flag attributor disabled, which says true by default. So if you want to run the attributor in the O3 pipeline, you have to say attributor disabled false. If you want to run it from the command line, you also have to say that, because otherwise you can spawn the pass, but nothing will happen. So now if we run that, expected top code. The return, like an empty module comes back. The attributor says, okay, told you, it deals with liveness. This is an internal function that is not called, so it's pretty much dead. So the attributor just deleted it and didn't even derive any information for it. So if you look at the debug output, if you want to see, there is not much output. It just didn't do anything. It never tried to like seed anything in an internal function before it could prove the internal function is live. So nothing actually happened here. So let's make it live. Define at next I1 C 32 pointer. No. Go and see. Now we 32. Where they call I32 pointer at test1 I1 C, and we have to give this a name. Okay, so now more happened. I did run the attributor again on this file, but now the function is live. And if you look, wait, let me pipe the output in something that does syntax highlighting. This is not nice. Okay, better. Break the lines. Okay. So what do we see? We see that the attributor only did deduce max object size, but a couple of other things, because, yeah, it runs by default with all the attributes. What do we pass as an argument? The alloc. For the alloc, we know it's no aliasing. It will not alias anything else in test 1. So it's annotated as no alias here in the call side. It's annotated as non-null, because allocars in the default address space are non-null. It's 4 aligned, which it actually is. It just doesn't say so. Dereferenceable and max object size 4, because the actual object size is 4. So all of that is derived here. And then you see that at the call, we also have the same information, because it was like propagated from the call side. And then it also propagated back down here to the recursive call. So even there is like the recursive call, we were able to annotate everything. Exactly. The return value is, what do we return? We will return for sure argument, because either we return argument or we go into recursion. So whatever we return, if we return is argument. So argument actually has a returned attribute. If you see that in the line above my cursor, it says returned. So argument is marked as it will be returned. And because of that, we find all the attributes that argument has also in the return type. Okay? Now, what would happen if we do something else? Let's build something else. Anyway. So let's have a global G. What's the syntax for globals? I always forget that. There you go. So let's return not recursion here, but we return the global G, which is also an I32 pointer, right? What happens now? Questions, by the way. Like you can ask questions if we look at this. A little less things that are annotated, because now argument doesn't have returned anymore, because it's actually not necessarily returned. But the return thing still has non-null, align 4, dereferenceable 4, and max object size 4, because both the stack allocation and the global variable both have like size 4 exactly. So like even the combined state of both will have that property. So where does this now not work? So I said earlier, this is not. This is actually not what you want to do. Sorry. Why doesn't this work as you want it to? Let me find an example. Now I have to come up with something, huh? So. I32 pointer. And arc. And otherwise we take phi t. Okay, now we have a loop in here that, wait, and now we have to get rid of this call, otherwise we will be. Okay, now we jump to label t, which is a loop, and then either like loops around and at some point returns the phi value. Okay, so this should not work now. We should not be able to deduce what we actually want to deduce. Once I get the syntax right. Oh, it actually does. Strip pointer cast is too slow. Is too smart for me. How do I get rid of that? Sorry? Yes, but then if I do that, I will never be able to derive max object size because it will change through that. On the other hand side, we're supposed out of time? 5 minutes? Sorry? Oh yeah, but get element, the strip pointer cast will look through those as well. Yeah, it's too smart. Yeah, that's unfortunate. So we only have 5 minutes left anyway. So let's go back and I'll try, like, is there any questions here? So let's try, like, do 5 minutes of questions at the end. We had a couple, but maybe a few more. Okay, ask again with the mic, please.
So if I have realloc, then comparison of the returned value with the original value and do stuff based on the original value. I know that at this point my object is actually bigger, but it seems that you will use the old value.
What happens if you use the original value? That's a good question, right? If you basically, what we need to do here, which I didn't, but oh, you say it. Like this is all not, like this is just like me creating this. What you have to do is you have to say, this is the update impl. You say A, get AA4, AA, no capture. Oh, actually, you could just say, yeah. You can say no capture or no free. No capture is easier. This is the gray error. Get position. So give me just a second. I'll explain in a. Okay, so you say every time you update, you make sure that the pointer you're currently looking at has not been captured. If it has been captured, you give up on it. You don't try to deduce information for it. That is a way, like one way to get rid of that problem. It's probably not the smartest way, but if anything can change the object size, you obviously have to give up on that point. And the only things that can change the object size will always capture the pointer. Like for example, if the pointer goes into an int to pointer, in pointer to int, and then you lose track of that integer, which could then go into a realloc or whatever else, you couldn't, like it is, like as soon as it's captured, if the pointer can be, or the property can be modified, and it's captured, you have to give up. Like a lot of these properties actually like look for no capture, and only if no capture is set, they actually go further, because except if the property is like inherent and you can't modify, like you can't get rid of it. But if you can get rid of it and it is captured, you lose track. So you cannot say anything about it anymore.
So for free, do you actually check no free or also this no capture?
Both. No free, should at least. No free. Oh no, right now this is only no free for functions. The patch for no free for values, like that an argument is not freed, is accepted but hasn't landed yet. But the ones for functions only does this, which is check for all call instructions. And if any of the call instructions that is assumed live is not no free, give up. And realloc is not no free. So if there's a realloc in there, you're done. If like no free means that function does not free. It can still, like if you have a pointer, pass that to the function. Even if the function is no free, but the pointer is not no capture, it could still be captured and then freed after the function, like after the call to the function returned. But no free says this function and everything inside what it will call will not free the pointer. So if you want to reason about you pass a pointer to a function, and then directly afterwards it is still valid. Like dereferenceability is still valid because it wasn't freed. But if then things happen and the pointer was captured, you cannot say anything anymore. So it's all specialized to certain situations. It's all scoped, this information. It's only about the function, not what happens after. OK, I think we're out of time now. In case you're interested, please take a look at the patches that are pending. Please take a look at helping us. Please take a look at just using it. All of this, what I've shown you, or most of it, and all of it will be soon, is upstreamed. You can play around. You can see if there's any problems or questions. Just shoot an email to the list, and I'll hope to get a little bit more involvement here. Thank you.